I don't know how to do this, Kelly.
Okay, if you'll take a look at page 203, um,
Do it later.
yeah, the stuff that you've been working on, the gas laws for the basketball ladies and the folks at home that are not here today, Wolf's Law, right? Avogadro, Charles, what was, how do we do that volume first? I forgot. Yeah, Gay Saw. Oops. And ideal gas law or combined gas law. It's been over 30 years since I was in high school algebra class, and I can still remember using this. And then ideal gas law. Now, for all gas laws, you have to change your temperature in Celsius to Kelvins. And with the ideal gas law, you have R is 0.08206 Callie, and Dustin found a typo in the first set of notes I gave y'all. 0.08206 liters atmospheres per mole Kelvin. So what that means is, with the ideal gas law, you've got to make sure your volume is liters, your pressure is atmospheres, whereas on the other gas laws, it doesn't matter. You can leave it in torr, pascals, milliliters, whatever. It's just with ideal gas law because you got to cancel out these units in R. So that's what you guys are using for yesterday's assignment. It's due tomorrow. We want to look at gas stoichiometry today. And as always, when you hear the term stoichiometry, you should think factor label, because that's what we're doing. Let's remember what we introduced yesterday. Standard temperature and pressure is 0 degrees Celsius and 1 atmosphere of pressure, which is also what the pressure is at sea level. One of those problems said that in yesterday's homework. If it is at sea level, the atmospheric pressure is 1 atmosphere. So the standard molar volume at STP. And that always makes me think of Stone Temple Pilots. I know you don't know who that is. I quit making that joke many years ago. It shows my age. But remember, 22.4 liters of a gas for every 1 mole. So we're going to use that as a factor label. Other factor labels that we can use are density. And for gases, density is always in the units of grams per liter. Because as we saw with the mole box yesterday, gases occupy a much larger volume than the same number of moles of that substance as a liquid or a solid. Okay, so let's just get into it. Starting on page 203 is just a ton of different examples of different things that can be thrown at you. So we're just going to work through those today. And if you guys have a question, just stop me and holler at me. Okay, sample 11 is just real basic. It says a sample of nitrogen gas has a volume of 1.75 liters at STP. So how many moles of nitrogen are present? Okay, if you have something like that, you should make a note. Oh, and this is 511. What page did I say it was? 203. All right, so that's where we're starting. Okay, we have STP conditions, so that should tell you immediately that it's 22.4 liters per mole of a gas. Anytime you see STP, that should click in your head. So we're given a volume, and we're asked to change it to moles. That's all this is. So once again, stoichiometry means factor label. So we take our given, 1.75 liter, and we're going to change it with this. We're going to use that as a unit multiplier. We want to get rid of liters and change it to moles of nitrogen. So it's 22.4 liters for every 1 mole. So that means we divide it. We got 3 cichlids, so 0.781 moles of nitrogen. The textbook goes through and discusses the justification for this. It gives you a table at the bottom of the page that shows data for many different gases in which the volumes were measured at STP, and you see that they all are very, very close to 22.4 liters. Doesn't matter what type of gas it is, and we'll find out why when we get into kinetic theory tomorrow. Okay, any questions about this? Free, standard, garden variety, factor label, right? Okay, well, let's flip over to 204, and let's look at one where we have to deal with a chemical change. Stoichiometry, chemical changes, right, guys? Okay, quick line, I'm looking at sample exercise 12 on page 204. And it says that quicklime is calcium oxide produced by the thermal decomposition of calcium carbonate. Calculate the volume of CO2 at STP produced from the decomposition of 152 grams of calcium carbonate. Okay, so we've got a chemical reaction. It's one of those reactions that we had to memorize last year in chapter 8. We are given that the conditions are STP. Once again, that means 22.4 liters per mole of gas. And we are given 152 grams of calcium carbonate. And we're asked to find volume of CO2. All right, so where do we start? Yeah, can't do anything with grams. You got to get it in moles. So we're going to take grams of calcium carbonate and we're going to change it to moles of calcium carbonate. How are we going to do that? Molar mass. Okay, now what? Right, Sarah, we got to change it from moles of one substance to the other substance. What substance are we going to change it to? The CO2. So we're going to moles of CO2. Now, what will we use as this unit multiplier? Mole ratio from the balanced equation. Okay. Now what? Liters. Good, Lauren. We're going to change moles of CO2 to liters of CO2 with STP. That's it. That's what we need. So there's our plan, Stan. Where we started. We got 152 grams of calcium carbonate. These smart boards way too narrow. That's why I don't want to use it. Okay, 152 grams. We need molar mass of calcium carbonate. So we punched in off the periodic table, 1 calcium, 1 carbon, 3 oxygens. It tells you in the sample columns what?
100 of 3.0.
1 mole. All right, that's calcium carbonate. We are here.
Maybe 1 mole of calcium carbonate to 1 mole of CO2.
Good. Where'd you get that? Now, is it balanced?
Yes.
Good. Always make sure the equations are balanced, because sometimes they might not balance them in zoomed off. On AP, they usually always do, but always just be on the lookout for it. Okay. All right. So that gets us here.
STP. Change it to liters. Yeah. 22.
Don't close your books. And that way you won't be tempted to look at the sample problem. You can go back when you're studying and read the explanations. Let's see if we can figure it out without that temptation. Okay, so we punch this in. Make sure our units cancel. Okay, so we got 3 sig figs. Yeah.
31.1
Okay. So that's not so bad, is it? This is not bad at all. Okay, now for one that's interesting. Sample 13. On the same page. This is on 204 again. Here's the problem. It says, and you might want to take a peek at the reading prompt on this one, but then close your book back after you look at it. A sample of methane gas having a volume of 2.80 liters at 25 degrees Celsius and 1.65 atmospheres was mixed with a sample of oxygen gas having a volume of 35 liters at 31 degrees Celsius and 1.25 atmospheres. The mixture was then ignited to form carbon dioxide and water. Calculate the volume of CO2 formed at a pressure of 2.5 atmospheres and a temperature of 125 degrees Celsius. Huh? All right, so let's go through and pick this thing apart.
I'm writing down all of the information.
So we have data for 3 gases on this thing. We are burning methane and oxygen. So what's the first thing we need? We're burning methane. We're reacting. Yeah, we need the combustion reaction. Good, Aaron. So methane is CH4, oxygen, and what were the products? Yeah. It needs to be balanced. How are we going to balance it? Is it balanced?
Put a 2 in front of the H2.
Put a 2 in front of H2O? Yep.
And then 2 in front of O2.
Is that everything?
I think so.
Okay. All right. So we know for methane, we know that the volume is 2.80 liters. We know that temperature, we got to change it from 25 degrees C to Kelvin. Good. Pressure. Okay. Oxygen. We know Volume is 35 liters. We know temperature in Kelvins would be pressure. Okay. CO2. What do we know? We are asked for the volume. We know the pressure is 2.50. 398. All right. This is not the same as what you did in yesterday's assignment. This is a chemical change. So that means, what are all the properties of a gas? Volume, pressure, temperature, and what? All the properties of a gas that we're studying, moles. We need to know how many moles of CO2 that is. We don't know. We got to find out. Well, it's a reaction product. We have two reactants given. Anything scream out at you? When you
We use
have,
the PV equals nRT.
not yet,
Limiting reactant.
limiting reactant. We have a limiting reactant problem. Aren't you thrilled? I see it. Okay, it's not so bad. But yes, Sarah, we will use ideal gas. All right, so we need to know how many moles of methane we have, how many moles of oxygen we have. So that's where we'll use PV equals nRT. Okay, so for methane, for all of these, it's going to be what? PV equals nRT. How do we solve for all of N?
It'd be PV over.
Good. So, for methane, we have pressure 1.65 atmospheres, volume 2.80 liters, R 0.08206 liters, atmospheres, all Kelvin, and for temperature 298 Kelvin. Okay, will you guys punch that in, please?
The third for Stacy and Miss Lawrence. So you have to do just unmake this.
You want to do the same thing for oxygen?
What is the number of moles of methane?
0.189.
1.89? 0.189. Okay. Let's just write it over here. Chance punch in again. Okay. See if you get that. Pay attention. Remember, when you guys are punching this on the calculator, you got to use parentheses. This times this. Okay, take this product and divide it by the product of this. So that means you would have to do this times this, get that answer, divide, open parentheses, this times this, close parentheses, enter. Keep working on that. but it's the product of the numerator divided by the product of the denominator.
So would it be 3 sig?
Yeah, 3 sig figs. Okay, so if you guys will do the same thing, you do the same thing for oxygen and get how many moles of oxygen there are.
So the limiting reactant, we would use that. Or are
Well,
we finding?
hang on a second. Okay, so how many moles of oxygen?
1.75.
Yep. Okay, so limiting reactant. Remember how we did this before? Take each of these moles of gas and change it to your product. Whichever one forms the least amount of product is your limiting reactant. And that tells you how many moles of CO2 you got.
So we change it from moles of CH4 to moles of CO2.
Uh-huh. So 0.189 moles of CH4. And we need the balanced equation again. 1 mole of CH4 to 2 moles, wait a minute, 1 mole of CO2, right?
Yeah.
Okay. So it's going to be 0.189 of CO2. Okay, now take your given of oxygen, 1.75 moles of oxygen. Change it to moles of CO2. Got 2. Yeah, 0.875. So it's just okay, so now, okay, do you see what we did? You take each reactant and figure out how many moles of the product it would form if you had plenty of everything else. If we had plenty of everything else, 0.189 moles of methane would form 0.189 moles of CO2. If we had plenty of everything else, 1.75 moles of oxygen would produce 0.875 moles of CO2. Right? Well, which one is the least? No. Yeah, I know. So that means once this gets all used up, reaction stops. There's no chance that this particular reaction is ever going to form 0.875 moles of CO2 because once 0.189 moles gets produced, methane's used up, reaction stops. So this is what we use here. 0.189 moles of CO2. So now we can just focus on ideal gas law again. We know how many moles of CO2 we got. We know its pressure. We know its temperature. So PV is in our T. We are looking for V. So divide both sides by P. So we have 0.189 pressure. Notice your units. Moles cancels. Atmosphere cancels. Kelvin cancels. So we'll end up with liters, and that's what we need. So you punch this in.
2.47.
Yeah. So that one's a bit more involved. But it's still the basic concept of limiting reactant. The only difference is they put a gas spin on it, but, you know, instead of just giving you grams or moles, they give you pressure and volume and temperature, and you've got to use ideal gas law to figure out your moles. Other than that, it's just straight limiting reactant. Okay? So you want to pay close attention to this one. It's 5.13 on page 204. All right? Okay. Another thing that we can use is density. Density of gases are measured in grams per liter, and that gives us the next equation. It's on your equation sheet, I think. I'll have to go back and look.
DRT over P.
Yeah. Molar mass of a gas what's the D? Density, RT over P. T has to be in kelvins. There is a way to memorize this. What does the kitty cat do? Yeah, when he goes to the bathroom? Dirt over poo. So Renee McCormick, I stole this from her at one of her workshops. This is called kitty cat equation. Molar mass is dirt over poo. It's not mine, it's hers. I'm not that clever. But yeah, so let's try this. This is page 205, 206, exercise 5.14. I wish I could think of stuff like that. Okay, so on this one, it says the density of a gas was measured to be 1.50 atmospheres, 27 degrees Celsius. Okay, so temperature would be 300 Kelvin. And density is 1.95 grams per liter, and they want to know the molar mass. Okay, so we're going to use this equation, just plug it in. Okay, density is 1.95 grams per liter, R 0.08206 liters atmosphere per mole Kelvin. Temperature 300 Kelvin. It should be 2 sig figs. I didn't write it as such. And pressure 1.50. All right, check your units. Liters cancels. Kelvin cancels. Atmosphere cancels. What do we got left? Grams per mole. Is that the correct unit for molar mass?
Yep.
You betcha. So now we just punch it in. And it's customary, remember that we state molar mass to 2 decimal places. 32. So if you were to just say that, it's 2 sig figs, you would, I think, would be okay. Okay, that's it. It's dirt over poo. Questions? Okay. I wish my sister's cat would do that. They don't always do that. And then they'll stick in it. Okay. Huh? No. This is marathon because I'm gone Thursday and Friday. but I can work with you in a little bit. Okay, and I'm recording for the ladies, for you guys. Sadie got YouTube channel set up, so I'm gonna try to get this on the YouTube channel, and then I'll give it to y'all. Okay, I'll send it through Remind. Now, Dalton's law. Remember Dalton? John Dalton? What did he do? Atomic theory. He did a lot of experiments with gases, just like Boyle and Charles and Avogadro. Here's his law. The total pressure of a mixture of gases is simply the sum of the individual pressures of each gas. So P1 plus P2 plus P3 plus blah, blah. So like the total pressure of air right now would be the individual gas, and an individual pressure is called partial pressure. The partial pressure of nitrogen plus the partial pressure of oxygen plus the partial pressure of water vapor, yada, 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 yada. You just add them all up. Super easy. Okay, so let's try that. Page 207. This is exercise 15. Mixtures of helium and oxygen can be used in scuba diving tanks to help prevent the vents. For a particular dive, 46 liters of helium at 25 degrees Celsius, that would be what, 298 Kelvin, and 1 atmosphere, and 12 liters of oxygen at 25 degrees Celsius and 1 atmosphere were pumped into a tank with a volume of 5 liters. Calculate the partial pressure of each gas and the total pressure in the tank at 25 degrees C. Okay, so let's finish setting this up. Okay, so this is the data for helium. For oxygen, what do we got? We got 12 liters, 298 Kelvin, 1 atmosphere. Okay, for the mixture, I'll just come over to this side. For the mixture, we know the volume is going to be 5 liters in that tank. And we are, the temperature is going to be 298 Kelvin again. And we are asked to find the total pressure and then the partial pressure. That means the partial pressure of helium and of oxygen in these new conditions, in this new tank. Okay. Before we can find out anything, what do we need? We need to know how many moles of helium and how many moles of oxygen we have that we're putting in this new tank. So, PV equals nRT. Okay, so we do that for each gas. For helium, I'll just demonstrate with helium. We know to do the same with the oxygen. We've got 1 atmosphere, 46 liters. And 298 Kelvin. Okay, so how many moles we got? Punch that in. 1.88. We do the same thing with oxygen. Plug in 1 atmosphere, 12 liters over R times 298 Kelvin. And we get that the moles of oxygen, 0.491. Okay, these have been pumped into this new tank with a new volume, 5 liters. So how do we find the partial pressure of helium? Do you see what's been going on here? You've got, this is in one tank. It's been pumped into 1.8 moles of it has been pumped. I'll call them back. What do you have? I see who it is. Eva. Do I have what? I'll call her back. Okay, you've got 1.88 moles of helium. It's been pumped into this new tank. This new tank, you've got to send a scuba diver down, right? Okay, his tank is 5 liters. So you pump 1.88 moles of helium into this tank. So what would be the new pressure? You've got 1.88 moles now occupying 5 liters instead of 46 liters. You see what I'm saying? So how do we find the new pressure?
Would we just use that and plug it in?
Yeah. I'm going to erase this so we keep our givens. Okay, so our new pressure of helium is going to be what? nRT over V. And that's going to be, what was that, 1.88 moles? R. Remember our units, but I'm out of space. Our temperature is still 298. All over our new volume, 5 liters. So our this is called the partial pressure of helium. You punch it in and
9.19.
thank you.
Yeah.
That's atmospheres, right? Okay, now we got to do the same thing for oxygen. I apologize for running through this so fast, but you can go back and watch this video as many times as you want.
So with oxygen, would you just do the same
You
thing?
do the same thing with oxygen.
And then you add those two together to get the total?
Yay, yes. And that's all it is. Okay, so for partial pressure of oxygen, nRT over V, punch in, what is it, what was the, 0.491 moles. I'm just going to put R, that's 0.08206, right, I'm out of space. 298 Kelvin over the new volume, 5 liters. And that's a partial pressure of oxygen.
These are 2.25.
I got 2.4.
I got the 2.4 too.
Check
That
the
makes
math there.
sense.
2.40 atmospheres. Okay, so this is the partial pressure of helium.
6.
Okay, partial pressure of oxygen. Now to get the total pressure in that tank, you simply add them up. The partial pressure of helium plus the partial pressure of oxygen. So that's 9.19 atmospheres plus 2.40 atmospheres. That's Dalton's law. Mole fraction. Mole fraction, the symbol is the Greek letter chi. The Greek letter chi is just a funny looking X. So if you have the mole fraction of some gas, I'm going to call it gas 1, you simply take the number of moles of that gas and divide it by the total number of moles. So like in the previous problem, if we wanted the mole fraction of helium, we would take that 1.88 moles and divide it by the sum of moles of helium and moles of oxygen. That's all it is. So in the previous problem, we had what? We had 1.88 moles of helium, right? And we had 0.491 of oxygen. What's the total number of moles of gas? I didn't, so I'm not doing a sample problem now. 2.37. Okay, so the mole fraction of helium would be 1.88 moles of helium divided by the total moles. Notice that moles cancel. Mole fraction has no unit. So 0.793. And then do the same thing for oxygen. Mole fraction of oxygen, 0.491 moles over total. You punch that in. It should add up to 1. Sometimes it doesn't because of rounding.
It does.
Okay? We still have one more thing with mole fraction and gas collection over water. We will go over that tomorrow. Kinetic theory. Hold up. Due Friday. Now you will have class time to work on it. 49 through 71 odd in chapter 5. What is Friday though? 6. And then I'm going to give you an AP problem. I'll give you your lab notebooks back. You've got Thursday and Friday to do this homework, do the AP problem, get your electrochem written up, whatever you need to do. We will review Monday, test Tuesday. Sarah?